Continuing on with chapter 2, we're going to start talking about the parts of an atom and also the idea of isotopes today. Now, before you go any further, I want you to stop for just a minute and I want you to imagine what an atom looks like. If you could take an atom and you can make it big enough, you can see the parts of an atom, what does it look like? In fact, I want you to pause this video and draw that atom for me. If you want to, I've also linked a video, or I'm going to include a little video. It's called WKRP in Cincinnati, that talks about what an atom looks like. It's kind of cheesy, it's kind of older, but it's going to give you a good idea. Now, the idea of the atom, we talked about, it's developed over the ages. We've added more to it. We understand it a little bit more thoroughly than we did before. Not all the models are perfect. None of them are perfect, but each one is going to bring out some important concept of that atom. So let's talk a little bit about what the atom's composed of. Now, we talk about how the atom has 3 subatomic particles. Ooh, what does subatomic mean? Subatomic means that it's smaller than an atom. That makes sense. So an atom has 3 parts to it. Now today we know that there's more parts. You can get to quarks and strings and all sorts of stuff. But for us in this class, 3 parts to the atom. We have electrons, protons, and neutrons. The protons are the smallest. Now I have the mass listed in grams. Remember that exponent, that scientific notation. I have everything to the same amount. It's all times 10 to the negative 24th grams. It's really, really, really tiny. You're going to move that decimal 24 places to make a very small number. Now, your electron has a charge of a -1. So electrons are negatively charged. Your protons are positively charged, and it turns out their positive charge is exactly opposite the electron's negative charge. So protons are positive. Look at the mass of that. It's much, much bigger than the electron is. And what we did is because this mass tends to be pretty constant, we're going to give it a new unit name. We're going to call it 1 AMU. AMU stands for atomic mass unit, atomic mass unit. And then we have our neutron. The neutron, very similar in size to a proton. It's just a tiny bit bigger, but we had to go out 3 decimal places to see a difference. Later on, when we talk about nuclear, we're going to come back to that difference. And the neutrons have no charge at all. They're neutral because they're neutrons. Now, in the center of the atom is the nucleus. The nucleus is actually Greek for a term called little nest, if you go back and you start looking at where that term comes from. So, sorry, I forgot to grab my pen. So the nucleus, we can say that is a little nest. It's the center of our atom. And inside that nucleus, we have the positively charged central core. That means we're going to have our protons, all those positive things, and we're going to have the neutrons. And of course, your protons and your neutrons have the same size approximately. Protons are positive, neutrons are neutral. Well, something to think about. How is it that you can have something with all these positive charges and neutral charges and they don't repel each other? That's a discussion for another day also. Surrounding that nucleus, that little center core, are going to be our electrons. Now, the electrons we know go in it's not a random order. There is some rhyme and reason as to where they're at. But it depends on what model you look at. So on the left, on the bottom, we have the Bohr model. And the Bohr model, remember, it was the planetary model where the nucleus is in the center. Looks like a little sun. And then the electrons are going to be in orbits around that central location. Now today we know it's not a perfectly circular orbit. There's different shapes to the orbits. So it gets a little bit more complicated. And so then they came up with what's called the quantum model. Here's the quantum model over on the right-hand side. Again, the nucleus in the center. And then we have, well, where electrons are likely to be. A lot of times I'll compare this to, okay, we're going to play Pictionary. What am I drawing? Ooh, what's your guess? Well, hopefully you guessed it. It's the state of Kansas. I'm not going to win any awards for drawing. And we can say in the state of Kansas, there's lots and lots of people around Kansas City, and there's lots of people around Wichita. And maybe we're going to go up here to Topeka. Manhattan's over here. Lawrence is up here. I'm hoping I'm getting them in the right spot. Oh, no, Lawrence is on the other side. Sorry about that. We have Pittsburgh over here. There's Coffeyville right there, that one little dot. And we notice that there's not a whole lot out in western Kansas. Yes, you have Dodge City, you have Abilene, you have Hayes. There are cities out there, but there's not a lot of population. So there's fewer dots out in western Kansas. This is going to give us an indication of where people live. This gives us an indication of where electrons are likely to be. They're most likely to be around the nucleus, and then as you go out, they get a little bit more sparse. But there are certain places they like to be and certain places they don't like to be. That's the quantum model. And we'll see a little bit more about that here in a little bit. All right, on to the next slide. Now, the nucleus is very, very small when compared to the rest of the size of the atom. On this one, it talks about the hydrogen atom, that the atom diameter is 100,000 times larger than the nucleus. You'll see different amounts on that depending on what resource that you're looking at. But here is the example that I was told a long time ago, and it really made an impression on me. So I'm going to see how it works with you. We're going to imagine that we're looking at a hydrogen atom, and a hydrogen atom is the simplest atom you can have. There's one proton, there's one electron. There's usually not even neutrons to mess with, so just a proton and electron. And we're going to imagine that that proton is the size of a basketball, because we want something that's going to be easy for us to imagine. So go ahead, pick up your electron. You got your proton right there. I say electron. Pick up your proton. Your proton's the size of a basketball. Now, if this is the proton, where's the electron at? Is it in this room? Is it in the building I'm in? Is it on campus still? Is it even in the same town? Is it in the same state? Where is it at? Well, what I had read before is that if you can imagine that this is the proton, that size, the electron is about the size of a grain of rice, so much, much smaller. And it would be located about 15 miles away. So back in Edna, where I live, there's a little grain of rice whizzing by, and that's the electron compared to this proton. Now, if you'll notice between this proton and that little electron that's way, way, way far away, there's nothing. There's no air. There's no matter. It's empty space. Most of the volume of an atom is empty space. Most of the mass is located in the nucleus. So mass in the nucleus, space is due to the electron's orbit, but most of that space, that volume, is empty space. There's nothing there. Now, to help us figure out how many protons, neutrons, and electrons that an atom has, we've come up with what's called a chemical shorthand, and that's what you see on your screen. The X is going to be what element it is that we're looking at. So let's do an example. Let's look at potassium. Now, potassium, if you go to your periodic table, I hope you have a good periodic table printed out, you'll see that potassium is the letter K. So here's potassium, the letter K. Now, I know you're thinking potassium doesn't start with K. It's based on its Latin name, and we'll see that for a good number of our elements. So don't let that bother you. Choose a periodic table that has the English name written underneath, and I'll give you a link for that also. Now, every atom of potassium has the same number of protons. It has to. And we call that number, that's the atomic number, that's the number written on bottom. And for potassium, that's 19. And then you might say, wait a second. Potassium on my periodic table, it has the 19 written on top rather than bottom. That's just the way that the periodic tables like to write it. When we write it in the shorthand, we're going to write it on bottom. Now that part I don't have to give you. It's expected that you understand that potassium always has 19 protons. So again, that's the atomic number unique for every element that we look at. The number up on top, so on the bottom of your periodic table, generally, is going to be called what's known as the mass number. Now, the mass numbers that we're going to use for the chemical shorthand are always whole numbers. Let me repeat that. The numbers that we use for the mass number for the shorthand are always whole numbers. The reason for that is that we're always looking at one specific type of potassium atom. We're going to learn that the number of neutrons can vary. So we're going to look at just one type. So the top number may be different, and it may be different than what you see on the periodic table. So let's see what I've got here and what we can learn from this. So again, I have the element potassium. Potassium. Did you eat some potassium today? Good source is bananas. This has 19 protons. 19 protons. And the next thing you learn is that the number of protons will equal the number of electrons. Protons equal electrons as long as it's a neutral element. Neutral meaning that it does not have a charge. There's no positive and there's no negative. That positive or negative would be in the upper right-hand corner. This one is neutral. So we have 19 protons, we have 19 electrons. Then the last thing we're going to look at is the number of neutrons. Neutrons. The number of neutrons is going to be your top number minus the bottom. The mass number minus the atomic number. 40 minus 19. Oh, do you need your calculators? That's going to give you 21. So protons, electrons, neutrons. Protons, always unique for that element. It can be found on the periodic table if I don't give it to you. The electrons equal the protons as long as it's neutral. And your neutrons is your mass number minus your atomic number. And the neutrons can change depending on what isotope we'll define in the next slide or specific type of atom that you have. So let's have you try a little problem on your own. Again, pause it and then come back when you're ready. All right, so this one says how many protons, neutrons, and electrons in the following? And I have a chemical shorthand, and it has an example of an atom right there. It says U. U stands for uranium. The mass number is 235, and the atomic number is 92. Now, because sometimes it's difficult to type things in computers and in testing software and stuff, occasionally you might see this written as uranium-235, just like that. Don't let it bother you. Remember that bottom number, you can figure that out based on the periodic table. It's just that top number that could change. So you might see it, like I said, as uranium-235. All right, so let's get started. The number on bottom, that's going to give us the number of protons, 92 protons. That's also equal to the number of electrons because this is a neutral atom. There's no positive and no negative charge. Finally, to find the number of neutrons, we're going to take the top number minus the bottom number. Oh, I know that's a hard one for your mind just to think about. 143 neutrons. So that's 235 minus 92. Now, that top number, we said it could change. The number of neutrons may change. So your mass may change. When that happens, you have what are called isotopes. Isotopes are atoms with the same atomic number. Well, same atomic number means that they are the same element, but they have different mass numbers. So they have different weights associated with them. So down at the bottom, I have 3 different examples. These are all examples of hydrogen. They're all hydrogen, so they all have one. If you notice in the middle of each of their little nucleuses, there's one red dot. They each have 1 proton. They all have 1 electron in their outer shell. So because they all had 1 proton, we know that they're all hydrogen. But they have different numbers of neutrons. This first one has 0 neutrons. The second one, oh, see that little gray thing right there? It has 1 neutron. And the one on the right, it has 2 neutrons. So if we looked at the masses, this first one, it's over on the left, it says it's hydrogen 1. The second one's hydrogen 2. And then we have hydrogen 3. Now remember that 1, 2, or 3, that's your total mass. That's your protons plus your neutrons. We're going to add them together. Now, because these 3 are, I hate to say really common, but these 3, because they're hydrogen, are very well studied. We have special names for them. We can call it protium is your H1, deuterium's your H2, tritium's your H3. The deuterium and tritium, they deal with some in nuclear chemistry. So these are isotopes, and they're going to affect the mass of that atom. So if you have an H3, its mass is much more than if you had a H1. Now, with these 3 different isotopes of hydrogen, they're not in equal amounts. Your H1 is much more common than H2, which is much more common than H3. So this slide is supposed to give you a visual of that. It says for every 6,700 hydrogen atoms of mass 1 in the universe, there's 1 with a mass of 2. So it kind of gives you that visual. H1 is much more common than H2. And that can affect your mass, as you're going to find out. Yay, we're back to question time. All right, on this one, given the mass number, one should be able to deduce the specific element to which the number is referring. True or false? What do you think? Answer? False. The mass number is your protons plus your neutrons. That's not going to tell you what the element is. The specific element, you just need the number of protons. Because remember, your neutrons can vary. Let's try another one. All right, second question for you right now. Which atom contains 10 protons? Pull out those periodic tables. What do you find? What you'll see is that for 10 protons, correct answer is neon. Some of you may have selected boron because its average mass is closer to 10. Remember, that's mass, that's your protons plus your neutrons. We're just looking at protons in this case. We're looking for the top number on the periodic table, the bottom number on our shorthand to equal 10. That's going to be our neon. All right, yet another question for you. True or false? All atoms of the same element have the same number of protons. Again, true or false? Answer, that is going to be true. The number of protons determines what element you're looking at. The number of neutrons may change. That mass number may be different. Good job.